Hi everybody, my name is Time, and the topic of this talk is plug-and-play task-level autonomy for robotics. I'll introduce a system that was designed and implemented by myself and my colleague Dan Swissa under the supervision of our advisor, Professor Brafman. My research is about making AI planning more accessible for robotic engineers. So the agenda for this talk, first of all, we will overview some background about the current state of affairs in the autonomous robot development, some gaps we found. I'll introduce the AOS, our system, some general concepts. We will see a demo and talk about future work. So the current state of affairs. We interviewed engineers from two leading companies developing autonomous robots in Israel about the process of developing an autonomous robot. So what they first do, they implement the basic robot skills, things like navigation, object detection, arm manipulation, the basic skills of the robot. Now, of course, they want to achieve a high-level goal, like in this example, they want to collect all the toys to a basket, and they need some kind of control mechanism to schedule the different skills to achieve this high-level goal. What they actually do, they manually write the behavior policy using automatons, behavior trees, or just using code, and this is not simple. Why? Because robots, they are physical agents, and when you are activating the robot skill, its effects, they are not deterministic, and so you don't know what will happen when you are activating the code before you are activating it. And even after you are activating, you don't always know exactly what happens. Why? Because you receive a partial view of the world from the sensors, and sometimes the sensors, they are noisy, so even your partial view is noisy. So this makes it very hard to manually write sequential decision-making behaviors. So this is a challenge. And even after they succeeded to accomplish a good behavior policy, if something changes, like, for example, they are changing some hardware in the robot arm, or maybe now the environment changed, we don't have a single basket, we have two baskets, or the skill code was upgraded, then sometimes they need to write everything from the beginning and to experiment, and so this is a real gap and a real challenge for robotic engineers. So why don't they use AI planning? AI planning it has domain-independent algorithms, and what they can do, they can just describe their problem, and each of the basic skills grounded to the parameters of the skill will be an action, and they will let AI planning to schedule the different actions. So why not to do it? So it's not that simple. We tested and reviewed different systems, and we saw that there are gaps. What are the gaps? First of all, the current action description languages. AI planning, it requires a certain input that describes the planning problem, and it is usually described using action description languages. These are more logical languages with the predicates usually, and this type of description is unfamiliar to most robotic engineers, and it's not the language itself, the current ADLs, they are not expressive and compact enough to describe real-world problems. And you can also look at the paper presented here in AAAI about probabilistic programs as action description language that talk about this gap and our suggestion. The second gap is the abstraction gap. When you're describing a planning problem, you're describing it high level. It's more abstract than the low level code of the robot. You are only describing things that are relevant for decision making, and you have a gap and you want to actually activate the selected skill, then you need to ground it with the low level variables, and sometimes you want to transform information that received from one skill to another. So there is an abstraction gap. And also, we inspected the current planning and execution systems, and we saw that there is limited support for stochastic, partially observable domains. and these are key features, characteristics of robotic domains. And also there is a significant integration effort. So when the robot engineer wants to work with AI planning, it's not simple for him. And also the planning problems, they are described using the current action description languages. And as we said, they are limited for these needs. So it's not so simple. What we offer is the Autonomous Robot Operating System, the AOS. This is only part of a wider vision. So the AOS introduces a complete methodology and tools to bridge basic robot skills and AI planning. The integration effort is small enough so that a single programmer can make his robot autonomous within a reasonable time. What's a reasonable time? Depending on the complexity of the problem. What we are talking about, a few days if the problem is complex. It is an automated plug-and-play solution. What does it mean? The user should only document his skills, behavior, and also the environment and goals, and the system does the rest. What does it mean it does the rest? It stitches between his skill code to the system, and so no additional code is required to stitch between his code and the system, which is important for engineers. So let's talk about some concepts. The heart of the system is the documentation. We have 3 types of documentation files. We have a single environment file that describes the state variables, the initial belief. Sometimes the initial state is not deterministic, so you can describe it. Some extrinsic events that may occur, like changes in the environment that the robot did not invoke, and special states that are desirable or undesirable, the objectives of the robot. So this is a single file for the whole system, and for each skill we have 2 types of documentation. One is the skill documentation. It captures the high-level behavior of the robot skill. It's also called an SD file. And we have the abstraction mapping, the AM file. The AM file is used to bridge the gap between the planning problem and the actual robot code. And it is used to describe how to activate the code and how to translate the execution outcome to a discrete observation, something that the robot can reason with and update its belief about the current state. What is the current state of the world? Okay. How does it work? Well, the AOS exposes a web interface, and and when an integration request is sent, and based on the documentation, it auto-generates a code for this specific planning problem, which is compiled and executed, and then the system simply operates the robot. It's also a modular solution, so now our current solution, it works with the ROS1, but it can work with other robotics frameworks, and so it's only a support we need to do. The solution itself, the concept is it's not tied to any robotic framework. So let's look at a demo. In here we see we wanted to make a robot that can solve a tic-tac-toe problem. This problem is very simple, but it shows some of the advantages of the system. So all of you know the tic-tac-toe problem. So what we need to do, we need to implement the basic skills of the robot. So we are acting as the robot engineers, and we need to document our skills and to activate the AOS. So we have, first of all, we have 2 skills. The first is to draw, and we have a robotic arm, a Panda robot, a cobot, a cooperative robot in our lab, and we implemented a PID controller using the robot API, and also we implemented a detect skill. We attached an Intel RealSense camera to the robot arm. We took code from the web that can identify a tic-tac-toe board, and so we implemented, and this detect skill, what it does, it detects when the state of the board changes, like when the human play and the state of the board changes, and then it reports the new state. So this is used to allow the human to play. And the draw action, what it does, it draws a circle in one of the grid cells. So let's see the documentation. So first of all, we need to document the detect and the draw, and we have first of all the environment file. So the environment file we need to describe the state variables and the initial belief, the objective, and extrinsic events. So this is how it looks, and you can describe your look ahead, how much you want the robot to plan in advance. In here, the horizon is 10 moves, and also we want to describe the state variables. So the possible state variables, first of all, we have our grid cell, which is an array of integers for the 9 cells, and we also described an enum for the empty cell, a circle and the x, and another variable which is it the robot tone or not. And in here, in this experiment, the initial state is known because the board is empty. The format of this all of our documentation currently is JSON, but we are conducting user studies and we are improving it. But this is the current state. So after we define the state variables, next we describe the special states. What are the special states? These are the states where the robot is winning or losing, or it's a draw. So in here we can see that you can compactly describe the desired states, and everything is described in C++. Also, we are conducting user studies, and this may change in the future. And so what we see here, that if all the 3 cells for winning, they are marked by the robot sign, the circle, then it receives 10 points, and it's a goal state, so the game terminates. Otherwise, a penalty of 10 points if the human won the game. And also, we describe the extrinsic changes. What are the extrinsic changes? If it's not the robot tone, then the human mark one of the empty cells by its strategy. Okay, and now we will describe the draw skill documentation. We will only touch the draw skill, not the detect skill, because we don't have enough time. So this is the SD files. In here you can describe the parameters that this skill receives, and the dynamic model, how the state changes. Now, even though our problem we don't really know the current state, we hold a distribution over state when we are solving the planning problem, but in the documentation, the robot engineer can think, I know my current state, how will my state changes when I'm applying the certain skill with these parameters. And in here we can see that the skill that we have a single a single parameter, which is the O cell position, O cell P, which is an int, the cell we want to mark, and the user can also define what are the possible parameters. So it defines an array of tuples. In this case, you only have a single variable, so this tuple will only contain a single integer, but if you can have more variables, and each of these tuple of this skill in the planning problem, it describes a certain action that the system can select. Also, it gives a lot of flexibility for people that they are using action description languages. They can appreciate it, and also the people that experiment with other systems, they can also appreciate this kind of flexibility. Next. This skill has precondition. What does it mean? It means that I cannot select a cell. I cannot use this skill if it's only if it's my tone, and only if the cell I want to mark is empty. Next, I'm describing the dynamic model. In it, I'm just saying that if I'm marking an empty cell, then it receives an O, and that the tone it becomes the human's tone. In this case, the model response it's always it's going to be successful, and we will see what it means, this model response. And now we'll see the abstraction mapping. This section it connects the high level description of the planning problem to the low level skill code. And what we need to describe here is how to activate the code and how to translate the response to an observation, something that the robot can use. And in here we will see we have 2 types of observation, as we will see. Now, to do so, we describe something called local variables. It's to help the program express different information to do this the two tasks that this documentation file is supposed to do. The engineer is supposed to do with this documentation file. So first of all, the local variables, it can receive information from the parameters of the skill. In this case, we see that the cell to mark is the O cell P. So when the system decides to activate this skill, then the low level, we can take this information to use it to actually activate the code. And also we are describing here a local variable which is called success, and it takes this success, it receives the information from the response when we are activating the robot code. And you can see here the assignment code, you can see that you can put in the success and you are writing code, so you can manipulate the information which this success variable will receive using code. So it's very, very flexible, and these small differences, they are important for the engineers. Okay, and then in this case we have two responses, which is success and failed, and this variable, they are dependent on the local variable called success we defined earlier. And we are defining in here to activate the code. In ROS you have services, and in here it's a ROS service, so you can describe its path, and you can describe the different parameters. Also you can use code, and you can use the local variable you defined. So in here we are seeing how we are defining to activate the code and to translate its response. And let's look at the experiment. So what we see here, we are sending we activated the AOS server, and we are sending a request using this is Postman. It can send HTTP requests, and we can see that the robot is starting. And even though it's a simple problem, we can see that the robot is acting in a reasonable way to deal with its opponent, myself. Okay, so sometimes we want to change a skill behavior. We talked about it. The actuator hardware was upgraded, the skill software was updated. Maybe the robot is now acting in a different environment, that the skills, they behave differently, so we want to do it easily. So if in this example we want to say that the robot is having trouble to mark the center cell, only 50% chance, then it's very easy to change the dynamic model of the SD file of this specific skill. And also you can add that now it may fail, and we can see that the outcome, that the robot is using this information to change his policy. Now, even though the center cell, it's the best cell when you're playing tic-tac-toe, now it will try to win the game without using this cell, because if it's using this cell, then it has a 50% chance of failing. And now when it's very important to mark, it is trying, and it's not succeeding. So this is causing him to lose the game. Okay. Also, sometimes you want to change the game. What does it mean? I have my skills, they are documented, but maybe I want to achieve something different. So maybe a new instruction was received to the robot engineers from the product manager. Maybe this robot is supposed to support different user preferences. So in here, what we did, we changed the tic-tac-toe game. Now in this game, you want, when you marked a corner cell, then every adjacent cell that you are marking, you are receiving a single point to this cell, and also the opponent is receiving a point for this. And in here we are describing the new special states. Now in here we split the special states. Why? Because we have each one of them, it's a one-time reward. You are not constantly receiving it when this state is met. And we can see that the robot is acting by the new policy, by the new objective. In here it receives a single point, and I'm blocking it. And now it's blocking me, and I'm blocking him. Okay. So for future work, what we are planning to do is we want to integrate deep reinforcement learning to improve the generated policy. We also want to improve the system usability. We conducted a user study, and we want to make improvements and to conduct another user study. We want also to use probabilistic programming languages to improve the model parameters from the robot experience. And so for in this example, we had like the 50% chance of succeeding. And maybe the engineers it documented something, but maybe it's not accurate. So we want to learn a posterior to about this parameter and to improve the model based on the experience gained by the robot. Thank you very much.